news is that now we get to go on to some very pure theory. The bad news is that we haven't done the hard work here. The rest of my life interrupted. I'm now working with a company called Obsidian Systems, doing some cryptocurrency engineering and other work in Haskell. But I still think this is a really cool line of research, and hopefully it has a future. Now is a great time to thank the other names up here. So Mark Pastroni has been working in Denmark on choreographic programming, I believe, for over a decade now. Joseph Neer has been my advisor through 6 years of grad school. Xueying Quinn taught me Lean and fixed a bunch of my Lean code. It's unfortunate none of them made it here today. So 2 years ago, I claimed that select and merge choreographic programming languages can do all the same stuff as conclave and multiply located value programming languages, and vice versa. We still don't have an actual proof for that, and one of the reasons is because it's not a very well-defined claim. So what's a select and merge language? What are conclaves and multiply located values? And what actually is the nature of the equivalence we're trying to claim here? So finally, late in the afternoon today, we can define some of these terms. So when we say select, select is an in-your-language communication operator distinguished from the normal COM communication by the fact that its argument is always a static literal. And then merge is not an operation inside your language. It's a meta operator. It happens during the endpoint projection compiler pass or whatever. And its job is to merge the branches of a choreography, of a conditional, which you don't know which one you're going to take. And so merge will say, OK, well, if you do the same thing in both of them, just do that thing. If you're receiving a select in one of them, then that turns into a, then you'd better be receiving a select in the other one. And that's going to turn into a lookup table of offer and choose syntax, which comes from multi-party session types, or I guess session types more generally, perhaps. And then critically, if you're not in one of those two situations I just described, merge will fail. Merge is a partial function and will identify, hopefully statically, some ill-formed choreographies that cannot be projected. So Fabrizio Montisi wrote a textbook on choreographic programming, and the textbook CP language is procedural choreographies. It works exactly as I just described. He was also involved in the Core Lambda project, which was a functional choreographic programming language. And one of the follow-ups to that line of work showed that you can do a thing in Core Lambda called distributed choice types, where there are multiple owners involved in a tuple. And the behavior you get out of that is very much like, in fact, basically the same as a multiply located value. It's been my observation that once you have those, if you have select and you have something that acts like multiply located values, I don't think you need a communication operator. I think you can do that as syntactic sugar based on select. So this kind of sketches out a Punnett square. These are all select and merge languages, but some of them are limited to singly located values, and some of them have multiply located values. Some of them, although to be clear, I don't believe anyone has actually implemented this bottom row. This is a thing that I believe exists, but take my word for it. So we have communication as syntactic sugar. Can you do that same trick without multiply located values and get a usable complete language? I don't actually know. I think so, but I'm not going to claim that you can. And what's the difference between them in this direction? So when you have multiply located values in a select and merge language, the thing that lets you do is recycle knowledge of choice across sequential conditionals. So we go into one conditional, and the owner of that branch propagates knowledge of choice using selection to the participants. If you have multiply located values, then you can leave your conditional, do a bunch of stuff in the surrounding choreography, and then branch again without doing more knowledge of choice specific communication. But is that just purely ergonomic? Because the way you're supposed to use select and merge languages is that intervening stuff can just be duplicated across your branches, and they only have the one conditional branch that spans the whole choreography. So maybe that is a purely ergonomic difference. Let's do the same kind of exercise for conclaves and multiply located values. So a conclave is a in-language operator, won't always be called conclave, that lets you use a choreography with one census, with one set of participants, in a place in your program where you would expect a choreography with some larger set of participants, a larger census. A lot of languages that I've seen do have this, and it's implicit in the act of calling a subroutine or calling a function, and that's actually a really easy and reasonable way to do it. Multiply located values are more of a type abstraction, or you can bake them into your central semantics. The sort of pretense there, the abstraction, is that you can have one value which is known to multiple parties, and so in your program or in your semantics, maybe you don't want to copy that value across them all. We just say there's one value and everybody knows it. That's a multiply located value. What I've demonstrated in previous work is that these two things can be used as a knowledge of choice strategy without select. So that was my paper in which I described multi-core and a couple other implementations with Lindsay and several other people last year. Previously, Clore is a closure implementation which has a lot of the same capabilities, but it works a little bit differently. So they don't do broadcasts natively, they just do point-to-point communication, but they let the program update the types. So the set of people who own a multiply located value can change over the course of the program. The communication operator adds people to the list of owners, and in that context, your multicast is just a syntactic sugar for doing a list of sends. So that fills in two of the squares. You absolutely can do a conclaves and multiply located values language with both multicast and flow-sensitive mutable typing. Does that get you anything that you would need or that you don't have in the other systems? I don't think so. And then in the lower left quadrant, is there a useful language, a useful way of interpreting a conclaves and multiply located values system that doesn't have mutable types and also doesn't have multicast? I don't think there is, but I haven't ruled it out. So that covers kind of the big paradigms, the two phylum I've been describing. Phylum, phyla, phylas, I don't know. But that's not comprehensive. Like choreographic programming is getting to be a large and diverse field of study. So selection types are cool. You see those in Choral. First-person choreographies are pretty new and probably somehow related to multi-tier programming. If you start removing capabilities from conclaves and multiply located values, you get the version 1 of Chorus, which was presented a couple years ago. And if you keep deleting stuff, you get hascore. In my dissertation last year, I showed that the original multi-core API doesn't take full advantage of everything Haskell has to offer. And you can actually do everything in multi-core without any built-in notion of a located value at all. All you need is the conclaves. And I don't think that that is specific to Haskell. I think that that relies on the notion of choreographies as data. So we know programs are data. But if your choreography is data, then a multiply located value is just a special case of a choreography. And then predicate transformers is up on top because although I don't think anybody's like using those implementations, their knowledge of choice strategy probably is dominant in the sense of subsuming everything else. Probably. So let's go back to the idea of what does it mean to translate? What's our equivalence relationship that we're after? Bisimulation would be great. So if you can do a step there, you can do a step in the equivalent translation. But I don't think it's promising. So if your conditional operation is something that you do semantic steps to evaluate, then in select and merge, first the owner branches, and then they send knowledge of choice related communication to everybody else. In conclaves and multiply located values, you do your knowledge of choice communication first, and then you branch. Yes, so confluence is your next choice. We can show that the two translations are going to end up in the same place, which, yeah, I think that's probably pretty straightforward, but it's also not really what we care about. In choreographies, the communication is kind of what we care about. The final evaluation in most systems is an afterthought. And even if it was just you want the output value, the intermediate communication has security implications, has performance implications. So confluence is not really the thing that we want. And also, once you support recursion, it's not going to be that much easier anyway. What I think we can show is some sort of eventual agreement on the intermediate values. And it's going to take a sec to explain what that means. So the first thing we want is all of your communication and also all of your local computation should be binding variables, because the variable states, the assignments to the variables are the thing that we're going to track. Normally, select in most languages doesn't bind a variable, but it's data over the wire, so we got to track it, so it needs to bind a variable. Since we're doing recursion, and also maybe you just want mutable state, so you can write to variables more than once, that's fine. And however, if you're writing to the variables more than once, then if I see x equals 5, I shouldn't have to worry about whether that was a message you received or something you computed locally, because those have very different implications. And whether you sent something over the wire is one of the things we're trying to show equivalence about. So we add to our type system both the owner and the originator of all data, and that way we can lock in if x is a message received from Bob at Alice, then everywhere x gets assigned, it's that message. It's going over that channel. Variables are kind of like channels. On the other hand, we don't, I'm skipping to the last bullet here actually, we don't necessarily need to support multiply located values in the semantics. Our type systems can do that and guarantee that they all check out, but at the semantic level, it's fine, just copy the values across parties. So that gives us kind of, when we think about our variable store, the state at any given point of the program of all the variables, you can think of it as having two dimensions now. There's the name of the variable and what party it's at. But then we're going to add a third dimension, because our semantics, when you do a write to a variable, you're not just going to overwrite its value, you're going to append to the list of all values it has taken on. So the ongoing behavior of the program will only ever look at the head of that list, but what you get out of your whole evaluation is the trace of every value that every variable was assigned to. And this is kind of what that looks like. I haven't shown here the actual choreography that is taking steps. I've shown the variable store. So there's 5 variables owned by 3 different participants. And there are 3 possible steps that I've said this choreography can take from here. So P is ready to evaluate Z for the first time. And so we can do that. Q is ready to evaluate Y for the second time. And so we can write 5 in there. R is ready to evaluate W for the second time, so we could step that way. The thing that should stand out about this is that when Q stepped and wrote 5, we put 5 in for Y as well, even though P is not, sorry, we put 5 in for P dot Y as well. But P is not ready to evaluate Y for the second time. So we don't actually have, and the reason why I say that we can do that is because I'm talking about the central semantics where we paper over some of those differences. And in order to get agreement with our network semantics or distributed semantics, we need to say, okay, like what actually is the relationship between the two? It's not one-to-one. It's this more subtle kind of coverage, eventual coverage. If you can bind a variable in one of your semantics, then there's going to be a corresponding binding that can happen in the other, and vice versa. What's this going to let us do? We want to define representatives of all the paradigms I tried to lay out in some sort of schematic earlier, so that we can show translations from one to the other and correspondences of the possible variable stores that can result out of their computation. And then if those correspondences are at all well behaved, we can start showing transitive either dominance or equivalence classes amongst them. I think mostly equivalence classes. And then we can talk about what is our strategy for doing that. The strategy that I'm proposing is to define one big language that does as much of it as possible. So we have one syntax, one concept of endpoint projection, one semantics, and some degree of type checking that supports communication, multicast, multiple located values, select and merge, and hopefully, or I should say, maybe some other bells and whistles. I think we can put predicate transformers in there as well. And then the concept would be, when I say representatives of the paradigms I showed earlier, we have sub-languages, a static analysis, a static check that you can do on one of these programs to say, yes, this fits in the Conclaves and MLVs paradigm, and whatever it can step to semantically, that satisfaction will be preserved. So it's a member of this sub-language. And then our translations say, okay, given something that passes that static check, we can translate into something that passes this other static check, and the space of variable stores that you get out of executing either of them is going to be the same. We haven't done that. How am I on time?
You're doing, let's see here. You have about 10 minutes, including questions.
Okay, well, I'm done.
Well, we have plenty of time for questions. So, questions?
So in the eCoop paper about core lambda, there is a way to, like a very loose sketch of how to express a distributed agreement type in a language that only has, sorry, not an agreement type, it's a multiply located value type.
Yep.
In a language that only has select and merge. But it was just a sketch. So one thing that's unclear to me at this point, is that actually sufficient to fully express all the expressivity that you want out of multiply located values? Is that already a sufficient translation, or is there stuff that you can do that we can't do?
It probably depends on what it is that you want your language to do. So core lambda is a lambda calculus. It has a kind of algebraic data types in the sense that it's got unit, it's got tuples, it's got choices. And if that's all you want, then I do not see any reason why you can't do whatever you'll be doing with multiple located values in that system. Actually performing the translation, nobody's written it out. It's not as easy as it first looks because you need to, so the way you represent a multiply located unit is by a tuple of units. The way you represent a multiply located choice is by a choice of tuples. And so how the structures get lifted is not, well, nobody's shown it exactly yet.
But you think that it is possible?
Yes, I think it's possible for that case. If the data type you want to represent is a function or a choreography, you might need something more powerful. You might need something baked in. But in the case of choral, I think you probably have more options because you can represent these more complex data structures.
More questions?
Hey, thanks for the talk. On your first slide, you asked, what do we mean by translated? Like, what's translate? And maybe to phrase that question differently, to phrase the question in terms of the equals sign, we could ask, what does equals mean? And so, I guess, what do we mean by equivalence, right? Like, one question is, do we care about like the same externally observable behavior, right? And you kind of got into that a little bit when you said, well, no, we also care about the intermediate results and the side effects and so on. But another thing we might care about is efficiency, like communication efficiency. So, and it seems like they wouldn't be equivalent in that regard, but maybe you could comment on that.
Absolutely. So my assumption has been that if you are communicating the same amount of data between the same pairs of parties in the same order, there shouldn't be differences in efficiency. Now, right off the bat, that relies on the assumption that all of your performance bottlenecks are in your communication. which might not be true. And also, like, maybe it's wrong. Like, I think it's true. So my assumption has been that we can represent all of the communication as a trace, as part of our variable store trace, and that kind of covers what we want. And since the communication is included, and also the order should be included, because that has security implications, so that should cover our performance concept. But like, there's other concepts of performance.
So I have a question. So these this idea of looking at the possible traces that the choreography can produce, including like what communications it does, is something that I've thought a little bit about with some students. Work that ended up transforming into something completely different. So,
As it goes.
But we were looking at it in the context of proving deadlock freedom, and so I'm wondering if you've thought at all about that in this work.
So I've been assuming that you want deadlock freedom, and
Like, have you thought about using the traces to actually define what deadlock freedom is, or anything like that? In any?
So I guess there's kind of two different things that I've defined and sketched out and begun building. One of which is sort of the computational model of here are some traces. And we probably could define deadlock freedom in terms of that. However, I've been thinking about it more in terms of the actual language that operates within that computational structure and being able to define deadlock freedom in the usual sense of if this thing is projectable and if your language, if any program in your language passes whatever minimal type system the language has and also is projectable, then it will have preservation and progress and correctness of endpoint projection, and those together give you deadlock freedom. Could you define that in terms of the underlying computational model? I haven't tried.
Any other questions? All right, Dan?
One thing I was confused about when you were dismissing the concept of by simulation, you said that that the order in which you do evaluate the guard of a conditional is reversed. In one case, you send and then you evaluate, and in another case, you evaluate the condition and then you send.
Yes.
But I mean, that seems like too fine a level of granularity. I don't care when we're evaluating. Like, I consider that like a tau transition, and therefore it doesn't matter if you do it either way. What I care about is the sequence of communications that I'm observing. So couldn't you do like a weak by simulation instead of a strong one?
Yes, well, maybe. I think if your weak by simulation is like you do big steps up till communication and then you are all set, you do weak steps up to communication, and then the communication is the thing that needs to match up. I don't know, because like in a Conclaves and MLVs language, the communication that enables knowledge of choice at the time of branching could have happened arbitrarily early in the program. And in a select and merge program, the communication that allows knowledge of choice can actually happen, like a lot can happen between you branch and then somebody needs to know which branch they're in. In fact, they can participate in the branches as much as you like before they actually learn which branch they're in. Yeah. So, like, no, I'm not going to claim it's impossible. I'm going to claim it looked hard and I didn't do it.
All right, let's thank Mako again, and can the next speaker come up and sit up?